Okay, what are the important chemical properties of 15th group elements? First one is important one, reaction with hydrogen atom or hydrogen. Okay, so 15th group elements. What are the 15th group elements? Nitrogen, phosphorus, arsenic, antimony, bismuth. These 15th group elements, whenever they react with the hydrogen atoms, they form EH3 type hydrides. Where E is equal to nitrogen, phosphorus, arsenic, antimony, and bismuth. Okay, so they forms hydrides. What is the general formula of hydrides? EH3, NH3, PH3, SH3, SPH3, and BiH3. These are called hydrides. Okay. See, these hydrides, how we are preparing? These hydrides are preparing from metal compounds, corresponding metal compounds. See, preparation methods. Corresponding metal compounds on hydrolysis in acidic medium, then we are getting EH3 type of hydrides. For example, NH3 do you want to prepare means magnesium nitride. Mg3 and 2 you have to take. This is on hydrolysis in acidic medium. Then we are getting MgOH twice plus NH3. 2 moles of ammonia will get then 3 moles. Sorry, 3 to 6. 6 moles of water we need to take. Okay, let's see. pH3. Calcium phosphide, magnesium nitride on hydrolysis, then we are getting ammonia. Calcium phosphide on hydrolysis. Then we are getting CaOH thrice. 3 moles of calcium hydroxide plus 2 moles of pH3. Next, arsenic. Zinc arsenate Zn3S2 AS2 is on hydrolysis either in acidic medium or treated with HCl, dilute HCl. Then we are getting ZnCl2, 3 moles means 6 moles, then ASH3. So you treated with water in acidic medium or treated with dilute HCl, no problem. Next, magnesium antimonide. Then we are getting SBH3. Treated with 6 moles of HCl, then we are getting 3 moles of MgCl, magnesium chloride. Similarly, bismuth hydride also we will get. So these are the preparation methods. Another preparation method is also present. Metal trihalides. Metal trihalides, corresponding metal trihalides on reduction in the presence of zinc HCl are treated with lithium aluminum hydride, then we are getting corresponding hydrides of 5th A group elements. Another preparation method, let's see. ECl3. ECl3 where E is equal to nitrogen, phosphorus, arsenic, antimony or bismuth and bismuth. These are treated with lithium aluminum hydride. Lithium aluminum hydride. Then we are getting EH3 plus LiCl. Then we need to take 3 moles. Then plus 3 moles of LiH3. Okay, aluminum hydride we are getting. So where E is equal to nitrogen, then NH3, phosphorus, arsenic, antimony, and bismuth. This is another method for the preparation of 50A group element hydrides. 50A group element hydrides. So the 50A group element trihalides on reduction in the presence of lithium aluminum hydride are GHCl. This is the reducing agent. On reduction, then we are getting corresponding hydrides, 50A group element hydrides we are getting. Okay, so this is about preparation methods. Now let's see properties of this 50A group element hydrides. Already we know that properties, few properties. The first one is, first we will discuss about the structure. Structure of EH3 hydride. So the nitrogen or phosphorus, arsenic, antimony, they belongs to 50A group element hydrides. 50A means in that valence shell contains 5 electrons are present. Out of the 5 electrons, 3 are involving in bonding, and remaining 2 are exist as one lone pair. So that's why structure is 3 bond pairs plus 1 lone pair is present. Then total 4 electron pairs means sp3 hybridization and pyramidal shape. Bond angle less than 109 degrees 28 minutes. 109 degrees 28 minutes. See, among that nitrogen, phosphorus, arsenic, antimony and bismuth, if you observe that bond angles, NH3 has more than PH3, and then bond angle order. NH3 more than PH3, and then ASH3, and then SPH3, and then BiH3. Already this bond angle orders we are discussed in chemical bonding chapter. In chemical bonding in first piece, there only we are learned the structure and hybridization and calculations of number of bond pairs, lone pairs, these all. Okay students, let's see these 50A group element hydrides. Due to the presence of one lone pair on central atom, they act as a Levy space. They act as a Levy space. So due to the presence of lone pair on central atom, acts as Levy space. They act as Levy space. That basic character which can easily donate pair of electrons to the another molecule or another atom, they act as a strong basis. Among that, nitrogen is small size, then the electron density of nitrogen atom is more. The lone pair's electron density of nitrogen atom is more when compared to the phosphorus, as compared to the arsenic, as compared to antimony and bismuth. That's why NH3 acts as a strong base or more basic character when compared to that PH3, when compared to that ASH3, SBH3, and then bismuth. This is about basic character one. Now thermal stability. See, thermal stability depends on their bond length in between central metal atom and hydrogen. Stability. Stability. Stability is pH bond length increases, stability decreases. That's why the thermal stability of NH3 is more, and then pH3, and then ASH3, and then SpH3, and then VIH3. Thermal stability order also very important one. Okay, this is about thermal stability order. The next important point related to the properties of fifth year group element hydrides, that is reducing nature order. Reducing nature order. Reducing nature. So the reducing nature is mainly depends on thermal stability. Depends on thermal stability. The reducing nature is inversely proportional to thermal stability. So thermal stability decreases from top to bottom. Now what happens? My reducing nature increases down the group. So the reducing nature, bismuth hydride acts as a strong reducing agent. NH3, pH3, and then ASH3, antimony hydride, and bismuth hydride. This is about reducing nature order. Now, see among these hydrides, the melting points order as well as boiling point order we need to discuss. Melting points and boiling points. See, boiling point orders. If you observe that NH3 and pH3, NH3 having some abnormally has more melting and boiling points are present because NH3 can able to form intermolecular hydrogen bonding with water. That's why pH3 has less boiling point when compared to the ASH3, and then NH3, and then SpH3, and then VIH3. This is about boiling point order. And the same way melting point order is pH3, and then ASH3, and then SpH3, and then NH3. Ammonia has more melting points when compared to phosphorus, arsenic, and antimony. This abnormal property is due to NH3 can able to forms intermolecular hydrogen bonding with water, or can able to form intermolecular hydrogen bonding. Can able to form intermolecular hydrogen bonding. Okay. Due to the presence of intermolecular hydrogen bonding, what is intermolecular hydrogen bonding? The attractive forces between hydrogen atom and more electronegative atoms like oxygen, fluorine, and nitrogen. Then they form intermolecular hydrogen bonding. So, due to the presence of intermolecular hydrogen bonding, for any molecules abnormally, they have more melting and boiling points. Now, let's see solubility. Solubility in water. So among that, these all are covalent molecules, NH3, pH3, SH3, and these are not ionic compounds. But NH3 is soluble in water. Soluble in water. Why NH3 is soluble in water? Thus NH3 can able to form intermolecular hydrogen bonding with a water molecule. intermolecular hydrogen bonding with water molecule. Then that's why NH3 is soluble, but remaining hydrates are insoluble in water. They are soluble in organic compounds, but NH3 is soluble in organic compounds as well as in water also. These are the some important properties of 15th A group element hydrides. So first property is reaction with hydrogen atom. Generally they form EH3 type of hydrides: NH3, PH3, ASH3, SBH3 and bismuth hydrides. These are important hydrides. So among these all preparation methods of these hydrides, generally metal compounds, corresponding metal compounds on hydrolysis in acidic medium or as well as treated with dilute acids, then we are getting corresponding 5th A group element hydrides. And another method is also present, metal corresponding metal trihalides or corresponding element trihalides, NCl3, PCl3, SCl3, SbCl3, BiCl3, corresponding trihalides, trichlorides, treated on reduction with lithium aluminum hydride or zinc in the presence of dilute HCl, then we are getting corresponding 50 group element hydrides. So among these main important thermal stability and decrease basic strength order as well as reducing nature order. These three are very important. Among these also boiling point order also very important. So this is about reaction with hydrogen. Next, reaction with oxygen. Let's see. 50 A group elements combined with oxygen atom. Combined with the oxygen atom, they forms oxides. Generally, reaction with the oxygen. They forms two types of oxides present. One is trioxides. That is E2O3. General formula is trioxide. The second one is pentoxides. E2O5. Pentoxides. Trioxides and pentoxides. In trioxides, where E is equal to nitrogen, phosphorus, arsenic, antimony, and bismuth. So in these trioxides, oxidation state is +3 and here +5. The maximum oxidation state is +5. Okay, let's listen. Trioxides are more stable when compared to pentoxides. Trioxides are more stable when compared to pentoxides. Why trioxides are more stable? Generally, trioxides are formed in ground state electronic configuration, but pentoxides are formed in first excited state electronic configuration. In excited state electronic configuration, they forms pentoxides. That's why trioxides are more stable than pentoxides. In trioxides, oxidation number is +3 when compared to pentoxides. That's why oxidation number is increases, then acidic strength increases. Acidity order. So pentoxides are more acidic when compared to that trioxides. Pentoxides are more acidic when compared to that trioxides. Let's see in trioxides. Trioxide acidic nature. In a group top to bottom, what happens? My atomic size increases, then the acidic strength decreases. For example, nitrogen N2O3 has more acidic. Nitrogen, phosphorus. This phosphorus trioxide is exist in diametric form. Then P4O6 is more when compared that arsenic trioxide and then antimony trioxide and then bismuth trioxide. See, among that, this nitrogen and phosphorus has acidic character now. The acidic strength decreases from top to bottom. Arsenic and antimony are amphotic nature. And bismuth trioxide has basic character is present. Bismuth trioxide has a basic character is present. So it is very, very important. They are asking in objective examination. This is about trioxide's basicity order. Now nitrogen can forms +1, 2, +5 oxidation state containing oxides. So among that, what are those? For example, NO, nitric oxide, and N2O. Sorry, first N2O, nitrous oxide, nitric oxide, nitrogen trioxide, nitrogen tetroxide, and nitrogen pentoxide. Among these nitrogen oxides, here +1 oxidation state, here +2, here +3, here +4, and here +5 oxidation state. So the nitrogen can able to form +1 to +5 oxidation states containing oxides. Those are N2O, NO, N2O3, N2O4, and N2O5. Among these all oxidation state of same oxide, oxidation state increases, then acidic strength increases. So N2O5 is more acidic when compared to N2O2, O4, N2O3, and NO and N2O. So this is the acidity order of nitrogen oxides. Let's see nitrogen pentoxides. Nitrogen pentoxides have more covalent character when compared that nitrogen dioxide, because oxidation number or oxidation state increases, the polarizing power increases, then covalent character increases. And stability, if you are compared, the trioxides are more stable than pentoxides. Trioxides are more stable than pentoxides. Let's see one important point related to pentoxides. In the pentoxides, nitrogen, phosphorus, arsenic, antimony, they forms pentoxide, but bismuth does not form. Bismuth does not form pentoxides. Why? In bismuth, +5 oxidation state is unstable. +5 oxidation state is unstable. +5 oxidation state is unstable due to inert pair effect. Due to inert pair effect. Due to the inert pair effect, bismuth does not form pentoxides. Mostly it is forms trioxides only. So this is about oxides and their properties. Okay, let's see halides. Third one is halides. Reaction with halogen means 15th group elements or 50A group elements. Reaction with halogens. Reaction with halogens. What are the halogens? Fluorine, chlorine, bromine, and iodine. Those are called halogens. When they combine with halogens, they form two types of halides. Forms two types of halides. Two types of halides. What are those two types of halides? One is trihalides. Trihalides, the general formula is EX3. Trihalides. Generally, these trihalides are formed all compounds where E is equal to nitrogen, phosphorus, arsenic, antimony, and bismuth. And X is equal to fluorine, chlorine, bromine, and iodine is possible. Next, pentahalides. See, if you observe the trihalides, the presence of one lone pair is present, and they exist in pyramidal shape. They existed in a pyramidal shape. Pyramidal shape, sp3 hybridization. Pyramidal shape and sp3 hybridization. Okay, students. Let's see the bond angles. Bond angles. For example, nitrogen combines with chlorine, NF3, nitrogen, phosphorus, PF3. This in this bond angle, see nitrogen bonded atoms are same, and central atom electronegativity decreases, bond angle increases. NF3 is more than PF3. Nitrogen, phosphorus, arsenic, antimony, and bismuth trifluorides. This is the first point. And another point, the central atom is same, but bonded atoms electronegativity decreases, then bond angle increases. NF3, NCr3, and then NBr3, and then Ni3. So these are the different types of bond angle orders. Okay, then the trihalides generally they exist in pyramidal shape and sp3 hybridization, and they contains 3 bond pairs, 1 lone pair is present. See, among the trihalides, stability decreases down the group. Decreases down the group. Okay, and fluorides are more stable. Fluorides are more stable. Why fluorides are more stable? The fluorides, the bond length is less. If bond length is increases, then the stability will be decreases, because bond dissociation energy decreases. Stability is inversely proportional to bond dissociation energy. Bond dissociation energy, stability is directly proportional to bond dissociation energy. Bond dissociation energy increases, then stability will be increases. Bond dissociation energy decreases, then stability decreases. So, for example, nitrogen only C, NF3 is more stable when compared to NCr3, and then NBr3, and then Ni3, and then Ni3. See, these are among that fluorides are more stable. Let's see NCl3, nitrogen trichloride is more stable than phosphorus trichloride, and then arsenic trichloride, and then antimony trichloride, and then bismuth trichloride. Why, ma'am? See here, bonded atom halogens are same, but the central atom size increases, then the bond length increases, stability will be decreases. So this is about stability. Among that, trihalides easily undergoes hydrolysis, gives corresponding compounds. So out of that halides, fluorides can be easily hydrolyzed, when then chlorides, and then bromides, and then iodides, and the hydrolysis nature decreases down the group. So generally nitrogen and phosphorus can be easily hydrolyzed when compared to arsenic and antimony. Nitrogen, phosphorus, arsenic, they up to this top to bottom in a group, top to bottom, what happens? Hydrolysis character will be decreases. Let's see. Hydrolysis of trihalides. For example, NCl3. See, from nitrogen to phosphorus, arsenic, antimony, and bismuth and antimony compounds cannot be hydrolyzed easily. So hydrolysis character decreases. When compared to that, halogens or fluorides can be easily hydrolyzed when compared to that chlorides, and then bromides, and then iodides. So important, it's on hydrolysis. then forms NH3, ammonia. So 3 moles of water you have to take, then forms 3 HOCl, hypochlorous acid will forms. This is about ammonia. And phosphorus trichloride, PCl3 you have to take, is on hydrolyze to give H3PO3. Phosphorus acid will form H3PO3 plus 3HCl. 3HCl will form. At the same way, phosphorus arsenic ACl3 is on hydrolyze to forms arsenic oxide H2O3, H2O3, then plus 3HCl. Sorry, 6HCl will form arsenic oxide. As well as antimony and bismuth, they are partially hydrolyzed to give oxides. Antimony hydrolyzed to give antimony oxide, oxychloride, SbOCl plus 2HCl. These are partially hydrolyzed. BiCl3 is on partially hydrolyzed bismuth oxychloride, BiOCl plus 2HCl. These are very, very important. So hydrolysis nature in a group top to bottom decreases. And among that halogens means fluorines are present or fluorides are present. Fluorides can be easily hydrolyzed when compared to chlorides, then bromides, and then iodides. So I am taking examples of chlorides. Nitrogen, phosphorus can be easily hydrolyzed to give corresponding compounds. Arsenic forms arsenic oxide, antimony and bismuth forms antimony oxychlorides and bismuth oxychlorides forms. Bismuth, because their hydrolyzed nature is very less. So this is about trihalides. Trihalides, their oxidation state of central atom is +3. Pentahalides oxidation state is +5. So pentahalides has more covalent character when compared to trihalides. So trihalides having more ionic nature, when compared to the covalent character. Ionic nature and covalent character we can explain by using Fajans rules. Already in first PUC there only we are studying. Okay, let's see about pentahalides. It's very, very important one. Pentahalides. Pentahalides. That pentahalide general formula is EX5, where E is equal to, see, nitrogen NX5 does not exist. Nitrogen does not form pentahalides because, what is the reason, ma'am? Because absence of means nitrogen does not contains vacant p orbitals. Does not contains vacant d orbitals. Already we know that. That's why nitrogen maximum covalence how much I said 4. But nitrogen trihalides their covalence is 3, it exists. But nitrogen pentahalides never exist. Either NF5, NCl5 or NBr5 or NF5 does not exist. Now come to that phosphorus. Phosphorus can able to form all types of halides. Phosphorus, pentafluoride, pentachloride, pentabromide, and pentaiodide. Px5, where X is equal to fluorine, chlorine, bromine, and iodine. It exists. Okay. Next one is the remaining arsenic. Nitrogen over phosphorus, arsenic and antimony, and bismuth. Bismuth, if you observe that, bismuth does not form pentahalides because due to inert pair effect. Due to inert pair effect, bismuth in +5 oxidation state is unstable. That's why bismuth pentahalides never exist. But arsenic and antimony, they forms only fluorides. AsF5 and SdF5. Means mostly fluorides will form. Phosphorus, arsenic, antimony, they forms fluorides. But chlorides and bromides and iodides only possible with phosphorus. Why not arsenic and antimony? Arsenic PbR5 and antimony Br5 as well as arsenic iodide and antimony iodide and arsenic chloride pentachloride and antimony pentachlorides does not exist means because that around the arsenic and antimony, chlorine, bromine, iodine, the size increases. Size increases means to existence of 5 chlorine atoms or 5 bromine atoms or 5 iodine atoms is not possible. That's why arsenic, antimony does not form pentachlorides, pentabromides and pentaiodides. Only they forms fluorides only. Okay. Now let's see the structure of pentahalides. So generally, fifth A group elements in their outermost shell, they contains 5 valence electrons are present. The 5 valence electrons are involving bonding. Then there is no lone pair electrons. So EF5 they contains 0 lone pair electrons plus 5 bond pairs. Then total 5 electron pairs are present. 5 electron pairs are present means its hybridization is sp3d2 hybridization and trigonal bipyramidal geometry TVP. Trigonal bipyramidal geometry is present. Okay, sp3d2 hybridization. Okay, let's see PF5 phosphorus pentafluoride exists in solid state and gaseous state. But PCl5 phosphorus pentachloride exists